setups. And here we are setting up a graph with some nodes interconnected. And so we have, we create the graph parameters into an input file, which will be supplied to the algorithm. So here is where we talked about the hyperparameters. You can define these hyperparameters. So here we are talking about step size, number of shots for each task, and what kind of interface. The interface, I thought we already defined. Did we define here? No. Oh yeah, we're defining it further along the line. So this is based on, so that's a parameter here. We are going to define the interface itself. And we'll be using different interfaces via auto gradient, TensorFlow, or PyTorch. You can use any of them based on the selection. So there is a algorithm script itself, which is given here. We are not going to go into the details, but you can look at that if you want. So this is the actual Penny Lane program, which we will submit. So here you can see it's the device is selected based on the bracket qubits. That's the SV1, and these variables are defined. So if you're not using the console, you have to get some of these details from the job and use it within your program. So it's using QAOA using the QML library and adding the layer here. So this is the actual circuit that will be run. And right, so here we are going to use again the base framework. And we are setting the interface and define the hyperparameters as we saw before, and setting the device here. And so this is the API for actually creating the job using SDK. So you set the device, you get the source module. That's the file we have. And from within the file, what script we are going to run, the entry point, and you define the job name based on the time limits. And so this is the input data, so where you can provide the input path name. And now we'll run this. So this should create a job. So this is again using SV1. And we'll use, so now we've used a Penny Lane framework to view the results. Run the job. And you can, so this takes some time. So make sure you submit it, and then you can go back to the jobs and have a look at it. Yeah, so there are a couple running. I think this is the one I submitted. I can't tell from here because it's named based on the timestamp, and you can look at that. So take this time to maybe explore different options within hybrid jobs, and also the hyperparameter options.
We have Alistair on the call already, Jax.
Great.
He's ready whenever.
So after this, okay, yeah. So I think this is the part. This is the last part, and you can, if there are any questions, we can answer. There was
a question here. I'll get one of them. You can get the last one. In case someone wants to use a custom container when creating a job, is there a specification the custom container should satisfy to be run through AWS? You just need to define that container after you create it in ECR, the container registry service. And thanks for that, Jax. And after that, you can point your code to that ECR ARN or resource, and that's all you need to do to get Braket to consume it. Maybe you can paste that link in the chat so he can
So
refer
that's
to it.
here. There's also an example notebook which talks through the process for setting up the job. So what we would recommend is to make your life easier is if you go into this, there's a bring your own container one. And say there are instructions here. So one of the key things is either you can build everything from scratch or pull from the base container. So I think is there a Docker file here? I'm just getting there. Maybe I can go into this. If you look at the Docker file, so you can pull from this image, the base image, and then add your own packages, any additional you need, and build that way. So the instructions are here as well. So I'll paste this example. No, this is not going to work, but yeah. It's under the hybrid jobs, bring your own container. So that part will work as well. So you can detail instructions here. I was going to show something. Is this done? It takes about 7-8 minutes for this to finish. So this is running. So do you want to take a break before continuing with Alistair, or that's all I had to cover?
We can take a 5 minutes break and then we can start with Alistair. So we can get it started at 3 minutes past the hour or 2 minutes past the hour from now.
Perfect.
Or
So Alistair will be continuing. I'll be around if you have any questions. This as
yeah,
well. I'll stay and
great.
talk to you in a few minutes.
I can start sharing my screen now if we're ready.
All right.
Cool. Okay, should be able to see that, hopefully.
Just give me 1 second, Alistair. Just have one couple of things to say before you can get started.
Can you see the presentation?
Yes, it's looking good.
Excellent.
All right. One thing for Shada, I'm gonna share here on the chat window the instructions that you need to use to reconnect to your environment or to create your environment for the first time. Is as a Word document, no problem at all. You just follow it. The second thing I wanted to mention is that we have detected a little bit of an unusual activity in IonQ. Just want to let you know that if you're going to plan to continue practicing your tasks and your jobs with IonQ, there is a security setting on the event engine. We will not be able to do more than 10 shots at this point. If you execute any task that has more than 10 shots in IonQ, the whole account will get automatically shut down and all your resources tear down. It's a security measurement that we have. So just so you don't tear the environment apart for the rest of your colleagues sharing the same account with you, for the 5 of you, I want to ask you that if you are using IonQ, please keep it to 10 shots only, or else the account will be shut down. All right, that's all. Thank you. You can go ahead, Alistair.
All right, fantastic. Thank you so much, Juan. So, hello, my name is Alistair McLean. I'm a Principal Solutions Architect here at AWS, and I work in the Aerospace and Satellite team. I also, from time to time, get to do these immersion days, which is fantastic. I love doing them and talking to you about quantum computing. I do have a little bit of a cold, okay, so apologies if I'm not coming across clearly. Please just ask to any clarifying points or questions that you might have. Also, during this presentation, I do like a lot of questions. All right, and Juan and will help out with those to some extent. I won't be able to see the chat as I'm presenting, but I'll try and answer as many as I can. And if I don't know, then we shall find someone that hopefully does. So just a little bit of admin before we start. There is a lab for this. I'm going to upload the zip file and I'll show you how to do it once we get to the hands-on section of the lab. But first, there's a little bit of a presentation. We'll go through quantum annealing and what that's all about, and look at an optimization problem known as max cut. Okay, so many of you probably familiar with max cut. It's a good optimization problem to do on annealers. You can also do it on the gate-based computers as well, gate-based processors, but the annealers are particularly good at solving these types of optimization and hill timing problems. As I say, please just shout out or put in the chat any questions that you have as we go through. What we're going to do today as an agenda is we're going to talk about, well, what's the difference? You've seen now through, Jag's presentation, if you were on yesterday as well, you looked at quantum gate computing. We're going to look at annealers. So what's the differences, right? Why are there two types? What's the point? We're going to look into D-Wave quantum annealer. We're going to look at the structure of it. And then in the hands-on lab, we're going to get really, really familiar with the QPU variant, the variants of the QPUs that D-Wave has, how the qubits are laid out, why most of these problems turn into graph problems, and how to solve and set up problems on the machines. So we're also going to look at what it means to have an annealer and what you're actually doing when you run an experiment. and why it's important that you have all of this knowledge going into the hands-on lab, because it'll become very apparent in the results how to interpret those results. Okay, so first off, what is the difference between universal gate quantum computers and quantum annealers? Well, I've summarized a couple of the differences here. Obviously, there's a lot more technical detail, but for today's purposes, this table is very instructive. So in a universal gate quantum computer, ones like from Braket or IonQ, you can perform any quantum or classical algorithm, right, to some extent. In annealing, they're actually used for a much narrower problem set. Okay, so in annealing, you're used to just doing sort of optimization or hill climbing problems. It turns out that those are a very interesting class of problems, and they're very applicable to real world scenarios. But the annealers are more constrained in terms of the type of algorithms that they'll run. Today, universal quantum computers have tens of qubits. We talk about tens, maybe 100 or so, maybe a little bit more. But annealers have thousands of qubits. Okay, so there's a big difference there. So why is that? We also talk about noise and how that qubits are subject to noise today. There might be a time in the future where we have what's known as error-corrected qubits, but right now qubits are noisy. They change phase, they change sign, that kind of thing. So similar issues with noise for annealers. When you encode your problem as logic in a universal gate computer, you've seen that you use gates, you use logic gates to express these problems. For example, using a Hadamard gate, C0, CZ, etc. When you are using an annealer, that logic is expressed differently. So it's actually expressed very much similar to a graph. Okay, so you actually describe qubit biases, the weights and the coupling strengths between those qubits and how they're laid out. And you perform what's called a graph embedding in order to express your problem in a format that the annealer can handle and understand. Some of the algorithms in the universal gate land will be things like Shor's algorithm. It's very popular in popular science, Grover's algorithm. And then for annealers, these are different algorithms. So for example, optimization problems, sampling problems, those are the kinds of things that you would use an annealer for. And obviously the companies I've already mentioned, D-Wave are the annealers we're going to use today. And then the universal gate companies, there's people like Oxford Quantum Circuits, there's Rigetti, there's IonQ, there's more companies coming out all of the time. So we are going to make use of D-Wave's Advantage processor today, and you can access it via the D-Wave Leap API, which is a completely D-Wave API, or of course Amazon Braket, and it's one of the strengths of Braket that you can access multiple machines all from the comfort of a notebook and a familiar API. And indeed, you can change. There's two different D-Wave devices available. And you can change those interchangeably very easily and see the different experiments on them. In fact, I would encourage it as part of the hands-on section. But what we're doing, so to sort of concentrate on annealers, what they're going to do is naturally, as part of the physics of the QPU, is return what's known as a low energy solution. And that's a good thing because optimization problems almost always require the minimal energy of an energy landscape that you define, and the sampling process within the QPU finds out where that lowest energy point is. Now, usually that lowest energy point correlates with the correct or one of the correct answers for your problem. So what does that mean? Well, we'll see in a couple of slides exactly what that means, but keep in your minds that if you're not familiar with annealing, keep in your minds that what we're trying to do is set up this, landscape or this environment that has different energy levels, okay? And the QPU, the qubits on the QPU are going to be arranged in such a manner that we can get our result by sampling the lowest energy result. And indeed, probabilistic sampling problems require good low energy samples, okay? So let's talk a little bit about what we mean by energy. So when we start off, we have this idea of a double well potential, okay? And this is B, and it's an equal probability of measuring a state 0 or a 1. Okay, so when we start off with our problem, you have, say, 2 qubits, let's say, and you can put them into a state of superposition and they'll be equally likely to have a 0 or a 1. What happens next is, physically, we're going to apply magnetic fields in order to tilt that double well potential. And what happens is, during that process, because of the way that we set up our problem, the lower energy qubit becomes a higher probability result. So therefore, when you run your experiment, the correct result becomes this lower probability, and then therefore you can sample the lower energy result. So to maybe illustrate this further, if we were looking at a problem that had 2 qubits and 4 possible answers, if we were to map this in an annealer, depending on how we set the problem up, and you'll see how to set the problem up in a second, then the answer at the lowest energy configuration when we run our experiment is going to be the best answer. Okay, so it's very easy then, very natural that these low energy results fall out of, due to the physics of the annealing device, these low energy results fall out of your the problem that you're posing. Of course, you need to set the problem up correctly first of all, and that is also a little bit of a challenge, but we're going to go through it. We're going to do maximum cut, and I'll show you exactly how to embed a graph into the graph of qubits on the annealing QPU, run the experiment, get the results, and interpret the results correctly for what they are, so that you can see, okay, well, actually, we get multiple results all at the same energy. What does that mean? So we'll get there. So we're going to do max cut. So for those of you that aren't familiar with max cut, we're going to go through very quickly now, and I'm going to skirt around any mathematics because it's a Friday morning. Nobody likes doing mathematics on a Friday morning. That's not true. I enjoy it, but that's by the by. So what we're going to do is look at max cut, and optimization problems in general are ubiquitous, right? They're found everywhere in lots of different industries and lots of different applications: logistics, finance, oil and gas, pharmaceuticals, lots and lots of different applications to these problem types. Traveling salesperson is the canonical one. Maximum cut is really interesting because it enables you to have this graph, and then you're going to partition the graph into 2 sets. Okay, so in this toy graph that we have up on the screen here, we're going to partition the sets such that the total weight of the edges connecting the sets is maximized. And this is super important in a number of applications. Finance is one example, but there are many others. So in this case, what we would expect would be we would have a configuration. What we're looking for out of the QPU is a configuration of these nodes. It's going to tell us which ones are grouped together and which ones are not grouped together. Okay, and it's going to give us our 2 sets, right? And we're going to run the experiment multiple times, and the lowest energy result containing the 2 sets is going to be the right one. But what we're going to find is actually there's multiple ones. So let's get into that. What we're going to do is, as part of this, is define a QUBO, excuse me, and that's a quadratic unconstrained binary optimization problem. And it's actually really straightforward once you see the code, and you'll get a chance to do this yourselves. And indeed, a QBO kind of helps with many optimization problems. All right, so you have this idea of a quadratic cost function. You then have, number of binary variables, usually however many nodes there are or edges there are in the graph. And there's no constraints on Z, right? So you can have as many as you like. I mean, I suppose there's a physical constraint, but what we're going to do is set up our graph much like this. Okay, so we're going to describe our toy graph, and we're going to translate it such that we can represent it in the quantum computer really easily as one of these QBO arrangements. So how are we going to do that? So we need to be able to say, okay, max cut consists of, and again, we're not going to go into the mathematics here, but let's say we have this toy graph of 5 vertices, okay, and 1, 2, 3, 4, 5 edges, okay. We're going to give these all binary, these become binary variables, all right. And the W's are going to be, different weights or edges between the vertices. We can then translate these directly into what the quantum computer, what the D-wave annealer needs in order to run our QBO problem. So we're going to create these what are called quantum spin operators, and then we're going to run the annealing process. All right. Now this sounds really difficult. It's not. Once you see the code, it will become really straightforward. We're going to effectively do a graph translation problem. So we have this graph, which consists of our 5 vertices. We're going to translate it into a graph that can exist on the QPU. All right, so there's a translation step or an embedding step. And then we're going to run the annealing process. And the cool thing is that we get this energy landscape. This is sort of my interpretation of an energy landscape. At the bottom of this energy landscape, we'll find the results that correspond to the correct maximum cut. So let's go to the hands-on session, and we'll give you a few minutes to get set up with that. Okay, we've got some questions. Let's take some time for some questions because we went through the presentation a little quickly and everyone was very quiet. And we can talk about some of the questions here. Hold on, let me just try and. Okay, how far did we get? The QA, OA, and quantum annealing solves the same kind of problems. Yes. Oh, one's already answered. Okay, cool. As far as I know, D-wave QPUs are implementations of quantum annealing. Yep, exactly. Right. So now we're going to do this. Okay. So what I would like you to do is this zip file that I'm going to drop into the chat contains the lab. Okay. And I'm going to show you how to import that zip file into a notebook. And then bring up the notebook, and there's challenges for you all to do in that notebook. Now, you've all been extremely quiet. I'm pretty sure everyone's microphone's not working this morning. Are there any questions before we go into the hands-on section? Any questions about the presentation? Any questions in general? I'm going to stop my.
Yeah, you got a question there, Alistair.
Yeah, can you contrast gradient descent, quantum annealing? Not to any great mathematical specificity, no. But they're similar, right? So you're thinking along the right lines. So with gradient descent, for example, if you're doing stochastic gradient descent as part of maybe hybrid jobs or maybe as part of some kind of machine learning application, what you're trying to do is give the machine a target and for it to optimize a set of tunable variables. Okay, and then iteratively, it's going to reassess those variables in light of the target and sort of adjust after each iteration to try and align closely to the target based on a loss function. Okay, what quantum annealing does is kind of very different in the sense that the annealing process seeks to get similar. I can see how we're sort of comparing the two, but they are slightly different in that the annealing process looks for, I guess, a way to travel down that energy landscape in a slightly different manner. I guess we are, defining a cost function in the QUBO. So they are similar, but I wouldn't like to jump into the mathematics behind it. Because I don't know it, quite frankly. So
sorry to interrupt. I don't know, it's just me. I don't see the screen share any longer.
Yeah, I'm not sharing anything right now. I'm going to jump into my into my notebook right now.
Okay.
And I'll show you all how to access everything. So let me share my screen. Okay, can everybody see that? Jags, can you see that now?
Yeah, okay.
It's there.
Awesome. Right, brilliant. So what we have is, apologies, I didn't really go into too much of the detail there, Marciano, but you're right in the sense that it's a similar process, but physically they're very different, and mathematically they're very different as well. What are the typical timescales of an annealing process? It's very, very quick. It's on the order of microseconds, I believe, milliseconds. Yeah, gradient descents. Yeah, it's all about parameter optimization. It's about tuning, the variables that you can change via that cost function in light of the, sorry, it's completely gone out of my head. It's cold is is annoying. Yeah, absolutely. Great. Okay, let's continue down the road then. So in Braket, you'll be familiar with this. You can see all of the devices here. For this hands-on lab, you can actually use any of the D-Wave machines that you want. They're all available right now. I'm in North Virginia. You don't have to be. You can be in whatever region you like. They're all available right now. So we can use any one of these, but I'll use a specific one during the hands-on section. Now, I have a sort of a teacher's copy of the notebook that you should have unzipped, and I'll show you how to import that into your notebooks. So I'm going to go through with the answers filled in, but what I would like you to do is open up your copy, which won't have the answers filled in, and actually, work out the little challenges for yourself. Great. So what we can do here is you can create a new folder in your notebooks, and you can open it up. And then if you go to the zip file and you uncompress that zip file, you'll find there's 4 files in there. And what you can do is just drag them directly into that new folder that you created. Okay. and it should come up with everything that you need. So you can open up the dwave maximum cut.ipynb, and this is the student copy. Okay, so this doesn't have the answers filled in. Where are those files? I put them in the chat. Let me repaste them because we've had some questions since then. So that's the, if everyone looks in the chat, you should be able to download that zip file, download it. Yeah, download it to your local machine, and then what you can do is, I'll put my video back on. What you can do is then uncompress that, so unzip that zip file, and then copy the files that it unzips into your Jupyter notebook window. Okay, and just give me 2 seconds. Okay, how's things going? So if you have these files, I'd like you to bring up the maximum cut Python notebook. I'll be going through this teacher's copy. So if you want to just follow along and watch me go through the notebook myself, that's fine. If you want to do it yourself, then I would encourage you to use the student copy. You'll find these little ellipses in the code as we go that require you to put things in and have a think about things. If anyone has any problems, please put it into the chat. We can help you out. But it should be pretty self-explanatory. And watch me as I go through, and then you can get hints as well. Is everybody ready to begin? I'm going to take you through this entire notebook now. Excellent. Okay, let's start. So what we're going to do, yes, there is, Andre, there is a given a graph, there is a tool for mapping it into Cubo, and we're going to do this right now. So we're going to really jump into quantum annealing and graph embedding right now and see how it all works. Okay, so we go to the notebook. There's a lot of preamble here, and there's a lot of math about the embedding process and exactly how to use a Cubo or the equivalent ISIN form and what embedding actually means. From a sort of a layman's perspective, embedding takes one graph and translates it into another graph so that you can have the same information represented in graph A. You can superimpose that onto another graph, B, and it's a translation type of a problem. Okay, so what we're going to do is go through this problem, and I'll show you, first of all, the anatomy of the D-Wave QPUs, all right, and why this graph stuff is so important. So if you come down here, in your teacher, in your student copy, you're going to put in this ARN of any system, any of the D-Wave machines you want. In this case, I'm going to use Advantage System 4. You could use one of the others if you wish, but let's just stick to Advantage System 4. And you can see some of the device properties, okay? Now, these are pretty interesting when we print them out. You can see that we're running on Advantage System 4.1 with 5,760 physical qubits, 40,279 couplers, and shots in the range 1 to 10,000. All right. So what that means is that you've got this idea of qubits and couplers. Now, couplers you can think of as just chains between each qubit, and the couplers are programmable. They have programmable strengths, so that you can then define things like edge weights in a graph using the combination of physical qubits and these couplers. And that's exactly what we're going to do right now. But first of all, we're going to look at the structure of the D-Wave QPUs, because this is incredibly interesting and it's really pertinent to our problem type, okay, the optimization problem types. So we've got a graph within the QPU. So for the D-Wave 2000Q hardware, it's arranged in what they call the chimera graph structure. It has 2048 qubits. Now, I'm not using a chimera system. I'm actually using the Pegasus system, but we'll see that in a second. Now, these are the 2048 physical qubits are arranged into 16 by 16 unit cells of 8 qubits each. Okay, and the connectivity between those qubits looks like this in the image. All right. Now, what does this look like to you? Right? It's a graph. So if we have a graph problem, or if we can represent our problem as a graph, we can go through an embedding process to actually map the nodes of our problem to the qubits arranged in the QPU. Isn't that cool? Because what that means then is you run the annealing step, and it actually, because of the physics of the QPU, spits out lots of answers for you. And then you sample all of those answers, find the one with the lowest energies, and those usually represent the correct answer. Now, this is for Chimera. For Advantage, so Pegasus was the version they did afterwards. All right, so Pegasus is a more recent version, and now they're coming out with a new one that's not quite there yet. Okay, I think Marciano's having a little bit of a problem with the notebook there. You creating a new notebook? Okay, perfect. So the Pegasus hardware looks completely different, right? Because they've found more efficiencies, they've packed in more qubits into this QPU, and the Pegasus hardware looks like this, which is really weird in comparison to the Chimera. But again, it's still a graph. There's still interconnected qubits with couplers, okay? And you can still performing an embedding step between our problem, i.e. our max cut, and what is existing on the QPU. And this is the whole point. In this case, you know, these colored loops actually form qubits. It's a little bit, you know, more esoteric, but suffice to say that Pegasus is also set up about using these unit cells. And what we can do is visualize these within the notebook. So let's do that. So first of all, and again, in your student copy, you don't have this filled in, but I'm just going to go through this. You can go through this as well by yourself and play around and change the different numbers, and you can see the different graph types. But for a Chimera graph, this is the older style, 2 unit cells. So I've just done one row, 2 unit cells, look like this. All right. 8 qubits in each cell. if we want to build a larger structure or use more of the QPU for our problem, then we can do a 2 by 2. And now you've got these unit cells arranged into this grid. Indeed, you can have anything up to 16 by 16, right? That's the maximum size of a Chimera QPU, graph. The Pegasus graph, on the other hand, looks very different. Okay, so the Pegasus graph looks like this. Now, the reason for that, it's still a graph. There's still nodes. There's still edges. We're still able to tune them, to push and pull the magnetic field strengths between the different qubits. Remember from the presentation, we can do all of that. It's just a completely different structure because D-Wave found better ways to build larger machines. And indeed, that's, one of the most active areas of research is building large, stable, error-corrected quantum computers. And the sort of the holy grail of quantum computing right now is fully error-corrected, large-scale machine that you can run, arbitrary numbers of qubits on. But that's some way off. For now, with the D-Wave machine, the Pegasus graph used to represent, up until very recently, I think a month ago, used to represent their most recent graph type. They have now come out with a third graph type. How long have they been using Pegasus? I think 3 years, I want to say. Could be a little longer, maybe less. Yeah, I could find out for you. It's on that order. I'm wondering if we can see when these became available.
We only know the Braket started 2 years ago, but I don't know before Braket how long the system had been around.
Yeah, no, I don't know either. Yeah, so it's been available in brackets for 2 years, but they may have been using that for slightly longer. So what we're going to do now is draw a slightly larger graph. So in this graph, we have 2 nodes of Pegasus. A larger graph, oh, hold on, there we go. A larger graph of Pegasus looks like this. Okay, so again, you can see this motif that's represented and duplicated is the word I'm looking for. Sorry, this cold is really bugging me today. My vocabulary has gone out the window. But you can see this motif is duplicated throughout, and indeed you can ask for more nodes. So how do we do this? So how do we take our maximum cut problem graph, right? How do we take that and actually represent it using these nodes and these edges instead and still retain the same amount of information? Well, we have to go through a process called embedding. And embedding, there's a really cool part of the D-Wave API called Miner. And Miner is a part of the D-Wave API that actually finds this embedding onto their graph. They know the structure of their graph. Miner can take any graph, pretty much within reason, and map it to that Chimera topology. Okay, and that's exactly what we're going to do now. So if we take this toy graph, okay, this is just from the NX, the Python NX library, and we ask for a complete graph of 9 nodes. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. And complete means that everything's connected to everything else. Okay. This is just a random graph, and we ask it to draw. Now, yours might look different if you're doing this for yourselves, because if I run it again, you get slightly different. It doesn't matter. All we're saying is, give me a complete graph. There's no weights on the edges. Okay, they're all considered 1, and there's 9 nodes. What we're going to do now is find a way to map this random graph onto our Chimera graph so that we can represent it within the QPU. All right. So we're going to take the connectivity structure of Chimera on a 2 by 2 basis because we have 9 nodes. Remember, a single cell of Chimera consists of 8 qubits, So we're going to need more than one cell. So I'm going to use 2 by 2. So I'm going to try with 4, see what happens, all right? Then what we're going to do is use minor to find the embedding using the edges and the connectivity structure of the edges on the QPU itself. So this G here represents this graph here, and the connectivity structure represents the graph of Chimera that you've just seen further up the top. And now we're going to plot the embedding. Wow, what's going on here? Looks like some kind of toy that my children would have with all the different colors, but there's a lot of information in here. So what we've done is taken our random graph, okay, of 9 nodes and embedded it or performed an embedding on the Chimera structure. Okay, so we're representing the same information in that initial graph on the Chimera device. And what you find here, and this goes into a lot of the explanation here, is that qubits that are the same color represent one logical variable in the initial problem defined by the toy graph, the K9 graph. All right, so we're using more than one qubit to represent a single node of our graph. Now, this is really interesting because now you've gone from 9 nodes. We're using most of the 32 nodes available to us. All right, so this is not a one-to-one mapping. So this is actually a really hard problem, right, that minor solves for us in mapping our nodes of our graph to the graphs on the QPU device. All right, so let's just go through that again. The different colors here, and I apologize if anyone has any kind of difficulty seeing different colors, but the different colors represent a single node of our initial graph, because in order to fit the same amount of graph information, they've had to make use of more than a single qubit to represent a single node and represent all of the connectivity within this as well, the edges. It has to be able to use more than one physical qubit. So this is really interesting because you can see here that even if you have a relatively small graph, we're using quite a lot of qubits, okay? As you increase the graph size, the number of qubits increases. Now, I don't know the exact relationship because the minor process is, it's going to figure that out for us. But suffice to say that you're using many more physical qubits than you are nodes in your problem graph. Okay, that's really important. Now let's do it with the Pegasus system, just to show you the difference. All right, just to show you the difference in structures. Wow. Now compare and contrast this. This is really, really interesting again. So what I've asked for here in code is a connectivity structure representing 2 Pegasus cells. All right. We then take the same graph as before. We've made no changes to our toy graph. And we also use minor again to find the connectivity structure using the Pegasus system now. Now we can draw the embedding, and you can see here that the Pegasus representation is so much more compact, right? We're now using 1, 2, 3, 4, 5, 6, 15, 16, roughly half of the qubits that we had to use with the Chimera system. Now, this represents the fact that D-Wave were able to iterate and make their system better. For our toy purposes today, it doesn't really matter, but you could imagine if you're doing a larger problem, the Pegasus system is not only does it have more qubits, the qubit representation can be that much more compact. All right. So now we've gone from 32 nodes representing our 9-node graph. Sorry, 32 qubits representing our 9-node graph, or nearly 32, to just 16, right? So that represents a much more efficient embedding. Okay, any questions about that before we jump into max cut? Because that was a tour of the physical structure of the QPUs. Is there different embedded chimera graphs impact the timescale of the annealing process? Yes, the annealing process will take longer for larger graphs. That's the main impact. There are other, technical things that would cause the annealing process to last a bit longer, but in general, the annealing process is extremely quick, right? It's on the order of like milliseconds. Does that answer your question, Andre? Okay. Any other questions about any of this structure? Were you able to follow at home? Were you able to do it on the student copy? The student copy. Okay, so it doesn't answer your question. Feel free to come off mute. I want to make sure that we're answering your questions properly here. Apologies if I didn't interpret it correctly. Okay, we have another question here from Marciano. Is the benefit of using Pegasus representation with the lower number of qubits related to resource utilization or performance? Kind of both, really. I mean, because you're using less qubits to represent the same graph than the Chimera system, you could, theoretically, it's not going to be that case for all graphs, but theoretically, you could represent larger graphs in the Pegasus system than you could with the Chimera system, because not only does it have more qubits, the representations can be more compact so that you can make use of less of those physical qubits to represent your problem set. Does that make sense? Great, thank you very much for the questions. These are good. Okay, so we've gone through the structure, and I hope at home you were able to do some of this. Again, there's little hints and ellipses when you try and execute the cells, they won't work. Again, coming down to, here in the student copy, you can put in your own connectivity structures, that kind of stuff. I show you how to do one, and then you can go through and add those. But I hope you all get a feeling for, hey, look, D-Wave QPUs have got very different structures, and this is fundamentally, this is a graph embedding problem that we're going to go through. Okay, back to our problem at hand. So now what we're going to do is max cut. So as we said before, max cut takes a graph, undirected graph, with a set of vertices and a set of edges, and it's going to try to partition the vertices into two sets such that the number of edges between those two sets that are considered to be severed is as large as possible. All right, so lots of applications here: clustering problems, portfolio optimization, pharmaceuticals, lots of different applications here for maximum cut. So let's jump into it. We can run our imports as before, and I'm just going to use the same device as we set up higher up in the notebook. You can change this, by the way, if you want, to a different D-Wave machine and rerun the problem and see the different results, but they each get the same result in slightly different ways. Now we're going to set the max cut problem up. All right, so we have a little helper function that just draws a graph for us. Okay, this is nothing to do with quantum mechanics, right? This is just a little helper function that draws graphs. And now what we do is we're going to go through and we're going to create a new empty graph. We're going to add the edges from our toy graph. And our toy graph looks like this. Okay. And you should be able to see that somewhere. Okay, so Oliver has a question, and it's not a rookie question by any means. All questions are valid, right? Still can't grab what the link between the qubits means. Is it that you're able to execute a gate on both of them and not when they're not connected? So this hasn't got anything to do with gates at all. So this is a fundamentally different paradigm for quantum computing. You're still using qubits, but the couplers, the links between them, represent entanglement effectively, right? But the strength of that coupling is tunable. Okay, so it's a variable. So you have a node as a qubit, you have a coupler as an edge, then you have another node as another qubit, and the strength between them you can vary with magnetic fields. That's exactly what a coupler is. And by defining the couplers on the QPU in these graph structures, it makes it easy not only to manipulate and access couplers and qubits on the device, but also to embed graph problems and optimization problems into the QPU. So forget about gates for now. Okay, gates are great. I love gates. Everybody loves gates. But this is fundamentally completely different to gates. Very clear now. Great. Okay. Taha, thank you for your question. Yes, the shadowed nodes represent that these are not being used for our embedding problem. So the shadowed nodes here, and there's quite a few of them, mean that they're not part of our problem. They're not being represented as part of the embedding. Minor has not found a need to use them to represent our graph. However, minor in the Chimera system had to use many more qubits, and the shadowed ones here are not in use, to represent the same structured graph. All right. Does that make sense? Great. Awesome. Keep the questions coming. These are great. What's the meaning of the different colors? Each different color represents a single node of the graph. Okay, so our graph here, our test graph, our toy graph, consists of 9 nodes. For example, let's choose a random node. Minor's chosen to represent that single node with 3 qubits. Now it might not be this one, it might be a different one, but it doesn't matter. Each one here is a single qubit, but this node has to be represented by 3 different qubits in order to satisfy the number of edge constraints, right? The number of edges, so that it has the same level of connectivity in the QPU as it does in our toy graph. The different colors are arbitrary, that just signify different nodes. So you could map blue, for example, to one of these nodes. You could map red to one of these nodes. I don't know which one it is. It's kind of random, because if you run this again, they switch. All right, but the same thing applies. Like, you're using physical qubits to represent nodes. Okay, good questions. Right, let's dive into MaxCut. So MaxCut, we're going to use this toy graph here. Consists of 1, 2, 3, 4, 5 vertices and 1, 2, 3, 4, 5, 6 edges. All right. So what we want to do, and if you don't have that, it's maybe in the HTML file. So from your lab, I think I embedded that image. It doesn't matter too much. I can pull it out. Hold on. I'm just going to give you all of this. Okay. So this is our toy graph that we're going to use, and I've just dropped it into the chat. You should be able to see there. Okay. And we're going to represent this as a cubo. We're going to represent it as a graph, actually, first of all. And then we're going to translate that into a cubo. All right. So in order to set up the graph, this is the same as this isn't anything to do with anything quantum yet. We're just going to use the NX graph Python library, and we're going to add the edges from each node. So we're going to add edges from 1 to 2. So for example, add this edge. Then we're going to go and add the edge from 1 to 3, add this edge. Then we're going to add the edge from 2 to 4. You get the idea, right? 2 to 4. And this is how you build up the graph structure using Network X. Okay. And once we've done that, we can plot the graph, and we're going to see what that graph looks like. Okay. And lo and behold, it looks like this. Great. This is our problem. So we want to run max cut on this. And we can also set up our Cubo dictionary. So our Cubo dictionary is simply a Python dictionary with a way to represent this graph as a cubo. So I've printed it out at the bottom here. So let's spend some time on interpreting this. So what we've done is we've said, and the way you set up the cubo is kind of weird, but it makes sense for the QPU. You're penalizing nodes that are not connected. Okay, so for example, what we're doing here is we're saying if the node 1, 1, okay, 1 isn't connected to itself, there's no, it's not one of those type of graphs. This is an undirected graph. Then penalize it with a -2. Okay. If the graph is 2, 2, penalize it with a -2. The numbers are somewhat arbitrary. It doesn't really matter. But suffice to say that if they have negative values, they shouldn't be considered the structure of the graph. If they have positive numbers, however, this is a valid node. All right, so that's what this line here does. It says for every edge in our graph, if the graph, if the edge is valid, give it a positive number. Otherwise, just give it a negative number. And that informs the D-Wave API that we should ignore negative valued edges and only consider the positive values, because that's what our graph looks like. Okay, so for example, you can see here 1 to 3, right? 1 to 3 is a real edge in our graph, so that's great. So give it a 2, +2. 4, 4 is not valid. Penalize that. 2, 4 is a valid edge, so that's positive. 3, 4 is a valid edge, that's positive. 5, 5 is not, negative. 3, 5 is a valid edge, and 4, 5 is a valid edge. So now what we've done is build up a system of penalizations to describe our graph. So this is just another way of describing the graph. This just so happens to be compatible with this cubo idea. So now with our Q matrix, we've built this Q matrix, and the Q matrix just represents this graph in a slightly different way to doing it this way, for example. Now we can solve our max cut. So this is really cool. So with max cut, we're going to set up some QPU parameters. Now, I would play with these a little bit if you want. You can change the chain strength, okay? With this graph, there's no weights between the edges. So we're just going to use the same chain strength for everything, right? Doesn't matter. There's no, like these edges could all effectively just be one. We're going to run 20 samples. So we're going to run the same experiment multiple times and build up this energy landscape and then see which ones have the lowest energy. They'll correspond to the correct answer. So we set up running our Cubo. So we've already got our Cubo, we built it with Q. And then the D-Wave API is really nice because it can, allow us to input our Q matrix, change our chain strength and the number of reads, and bang, there we go. That's the sampling process. So in these 4 lines with Braket, with the Braket API, we've been able to say, okay, we're using the Braket D-Wave sampler, which is a class from the Braket API. We then specify our device, which is the Advantage System 4 again. And then we're going to use this embedding composite class from the D-Wave API. So we're going to use an embedding composite sampler. And then we're going to ask the sample to execute our Cubo with our QPU parameters up the top here. And then we're going to get our results. And that's it. The rest of this code really just, gives us our results and draws a pretty graph. But you can see here it's very, very, very easy. It's 4 lines of code in order to run this annealing process. So let's run it. So now this is going to Braket. Braket's then connecting to D-Wave, sending it the information, running the samples 20 times, and then bringing back my results. And then, bang, it's going to print them out. So this is really cool. So let's interpret these results. And you can go through some of this code by yourselves if you wish. We've got 4 answers, all at the lowest energy. Okay. The reason for that is that they're equivalent. Okay. So for example, if we make a cut and we get the nodes 1 and 4, for example, and yes, chain strength. I'd need to look it up. I believe it's to do with the coupling strength. Yeah. So here's a link to D-Wave's white paper on chain strength. Okay. And you can see here, this will take you through exactly what the chain strength is and why it and how it pertains. Okay. But effectively, it's a little difficult for me to describe, honestly. I'm not entirely sure. It's related to all of the coupling strength across the entire graph, basically. Okay. The maximum number of nodes that can be solved, I don't know. It's not quite that heuristic, no. I'm really not quite sure, but yeah, Gabrielle, hopefully that's useful for you. Apologies, I can't go into more detail there. Okay, let's keep going then. So let's interpret our results. So our results have given us back 2 sets. That's what we want. That's what the definition of max cut is. Great. And it's able to partition them into this lowest energy configuration by making 5 cuts. Energy numbers, by the way, are kind of arbitrary. But there are now 2 sets that will be the correct max cut. And then we can also graph it here and show you exactly 1, 2, 3, 4, 5 results in 2 sets, 3, 5, and 2, and 1 and 4. Okay, and that is a toy max cut problem on a D-Wave machine. So the discussion here goes into a lot more about the the results, but you can see here that these are symmetric, right? They're the same. 1, 4, and 5, and 2 and 3 is also a valid max cut, and again you get the symmetry happening there as well. If you do it more often, let's say like we run it more than 20 times, let's say we run it, I don't know, 40 times, you will eventually get slightly different results back. It's going to take a little longer. Yeah, okay, well, we'll get the same results. That's fine. Okay, that is the hands-on portion. Hopefully you can yeah, that's right. So graph embedding is actually a really hard problem. That's why we're using Miner to do this. I believe it's an MP problem. But Miner makes some assumptions, especially about the target graph. Like arbitrarily embedding one graph in another is a very hard problem, but we've already got the Chimera structure so that you can do that Miner embedding. Yep. Chain consists of the qubits that correspond to the same node. Right, gotcha. And the end of the annealing, see, this is wonderful. Yes, can you explain again the relation of values and the graph? Absolutely. So the whole point of max cut is to separate your graph into 2 groups, 2 sets. And within each set are the nodes of the graph that represent, if you were to do a maximum cut, what that would look like. So the results here represent nodes in each set. So we've done 5 cuts. We can do 5 cuts here, and you get the nodes from each set. Okay, and they correspond to the lowest energy. If we say, hold on. Trying to print out. Yeah, trying to print out more results because you do get more than. Okay. Regardless, here's our results, and we have the correct result at the lowest energy. So tasks and shots. So the number of runs corresponds to shots in this case. And it's a single task. So if I execute this guy, this is one task, and num runs is num shots. Yeah, that's right. So I'm executing one task with 40 shots in this case. If I turn that down to 20. Yeah. Okay, getting a lot of questions now. Hold on. I'm going to need some help here. So let's say how can we relate this to a problem domain? So let's take a marketing result, marketing clustering result. You might have, different groups of people or lots of different customer types, and you're trying to work out how to separate those into two groups. MaxCut could help you there. Okay, and then running this, for example, we might have, these vertices might represent two groups of people within that marketing problem. As an example, it could also represent, stocks in a portfolio that perform in a correlated fashion, right? It just depends on how you set the problem up. This is a toy example. Obviously, real problems will have much more complicated graphs, but those are the types of things that MaxCut is really good for, is separation of sets of vertices in a problem graph, because it's not always an easy thing to do. Yep, work. Yeah. Okay. All right. That's all I had. Hopefully that was useful and you were able to follow along at home. We can hang around for some more questions if you like, or Juan, what do you want to do?
That's exactly it. There is more questions we can
Juan, you're very quiet, mate. Flick the microphone.
Yep,
There you go.
that should do. I don't
There
have
you
my
go.
ear
Now.
here yet. I was just about to share the survey. Maybe that's the good thing to do now.
Yeah.
Let
Yeah.
me see if
Sorry, I
can.
didn't update the survey in the notebook, so don't use
No
that.
problem. Let me grab it. So.
All right. Thank you all so much. We'll stop sharing just now, but continue with the questions. These are really good questions, and it shows that you're really getting engaged with this type of solution.
What I would like you to do, please, is to spend literally 30 seconds, no more than 30 seconds, I promise, into that survey that I just pasted over there. It is critically
Please.
important for us to get that feedback, because this is what helps us to modify this workshop, and also will help us to justify to our bosses that this is a good thing to do and that we are doing a good job, or we are not doing a good job and we should change. So please try to fill that survey that I just pasted over there and give us feedback. If you have a little bit more time than 30 seconds and you want to write more stuff about your experience, that's even better. But if you want, just fly through it and give us from 1 to 5 stars or whatever that is. What you think is 5.
Just 5.
According to your experience in these 2 days. So you will have a chance to give individual feedback for Jax and for Alistair. So please fill the survey. Thank you, Nikos. I appreciate that. Oh, the link is not working for you. That's weird. Let me check again.
It's works for me.
Okay.
I'm not on
Yeah, it works.
VPN or anything.
Yeah, it works for me as well. Well, and this is it. I hope you enjoyed it, and stay tuned. I hope you start using Braket more now, and contact us if you need any help or you want to organize more particular with your company or their workshop, or you have a specific problem that you want to tackle. Reach out. Don't be shy. Thank you for your time.
Yeah. Thanks, everybody. Bye.
Thanks all.